Yo, what's good, Algebra fam? Welcome back to another episode of How to Algebra. Today we're diving into factoring. We're going to break down the polynomials like a boss. We have the AC method, where you multiply and split terms to factor those tricky quadratics. Then there's the slide and divide method. Slide the leading coefficient, factor, and then divide. Easy as that. Then we'll look at a difference of squares for when you've got two perfect squares separated by subtraction. And finally, we'll tackle the perfect trinomials, where you factor squares that complete the puzzle, basically. If you're ready to conquer factoring, let's get it. All right, so let's get right into the first example of factoring with the first method. All right, so this particular method, the AC method. Now, this is probably one of my favorite methods of all the different methods that there are, only because it's tried and true, right? This is the most basic idea of factoring, and it uses the GCF, right? The greatest common factor. It literally uses it, and this particular method works every time. I have a couple examples here. All right, so the first example. All right, so the idea, right? This is the reason it's the AC method is because when we refer to the coefficients as A, B, and C, right, we have to multiply A times C. So there's this little, I guess, X puzzle that some people like to teach. I don't know. I really like it. So you multiply A times C, and then you figure out the multiples of A times C that add up to the B value. And then the process goes on from there. But this is step one. This is the first part of the process. So what's happening is that in this particular example, we have A times C. So 6 times 3. And this is positive 18, right? Positive 18. And I need to figure out what multiples of 18, right? Factors of 18 that add up to positive 11. So when you're going through this list, the more you do this, the faster you're going to get, right? But if you don't know where to start, that's okay. Just start at 1, right? Everyone starts at 1. 1 times 18, 2 times 9, 3 times 6, 4, 5, 6 times 3. So once the list starts to repeat, this is pretty much it. Now, always remember that you have the negative versions also. In this case, we don't need the negatives, only because everything is being added. Okay, so these are all the multiples of 18, right? And we see which ones add up to 11. So 1 and 18 don't make 11. 9 and 2, 9, 10, 11. So 9 and 2 make 11. And 6 and 3 do not. So there's only one set, right? 2 and 9. So the way this is going to work, so from here, we're going to split the middle term, this 11x, in such a way that this is going to work. So watch. So 2x plus 9x. Right, 2x plus 9x equals 11x. Now you may say, okay, well, I can make 11, unlimited amount of ways. 10 and 1, 12 and 1. Well, if I subtract, but 10 and 1, 8 and 3, 5 and 6, right? All these different multiples of 11, but there's only one that will make this quadratic factor nicely. So we have plus 6x squared plus 3. So notice just the middle term, 11x, gets split into 2. From here, you split it down the middle, always in front of the third term's sign. So plus or minus. In this case, it's plus. So it's always in front of the plus. That's going to play a role here in a minute. Okay, so then focus your attention on just the first two terms, right? And we always talk GCF, greatest common factor. So there's 2, right? There's the greatest common factor number-wise, and then the greatest common factor variable-wise. Maybe it'll have both, maybe it'll only be one, right? Who knows? In this particular case, so looking at, they're both even. So the greatest common factor number-wise, I can pull out a 2. Then looking at the variables, there's an x common to both. So I can pull out an x. So 2x is the GCF for the first two terms. All right, what's left behind? 3x plus 1. Okay, so you always want to do a sanity check, right? Check yourself. So when you distribute, do you get where they came from? So 2 times 3 is 6, x times x is x squared, 2x times 1 is 2x. So yes, this is correct. Keep in mind in this process that when we start to factor the second side, right, 9x plus 3, we have to keep in mind that we're expecting 3x plus 1. Right? I'm expecting that to show up. Now, I don't want to write it prematurely, like right now, but I'm expecting it. So technically, if you wanted, I guess you could just write it in and then verify that it's correct. So I want to factor out the GCF of 9 and 3, right? 9 and 3. So there's a 3 common to both. So if I pull out a positive 3, and then is there a variable that comes out as well? No, just x, right? X is only on the first term. So the greatest common factor is just 3. So if I check myself, if I distribute the 3 back in, I'm going to get 3 times 3x, which is 9x, and 3 times 1, which is 3. So yes, this is correct. So now let's just say if you wrote 3x plus 1 in and you started to factor out the GCF, and all of a sudden when you distribute, it doesn't work, right? Like it doesn't give you where you came from. Well, then it's not factorable, right? Like you can't, unless you made a mistake. But for the most part, it should factor. And if it doesn't factor and you did absolutely everything correct, then that particular example doesn't factor. It's not factorable. Okay. All right. So now, again, applying the GCF, right? Because on the left-hand side, we have a term. And on the right-hand side, we have a term, right? Because notice we started with a trinomial. We went through the process, figured out what two numbers multiplied to make 18 that added up to 11. We split the middle term, the b term, into 2. And then we factor out the GCF of both. So now we have a binomial, right? We have two terms being added together. So what's common to both? Well, it's the underlined part in red. So 3x plus 1 is common to both. So I can actually factor out a 3x plus 1 because that's common to both, right? If I factor that out. And then we look at what's left behind. Here we have 2x plus 3. So 2x plus 3. Now, if you think about it, if you try to distribute, right, all of this, if you distribute it, you get 2x times 3x plus 1, and that's exactly what we have on the left. And then 3 times 3x plus 1. That's exactly what we have on the right. So to bypass all of this, right, like you don't really have to put this much thought into it every time. But once you see that the parentheses part matches, that's just one of the factors immediately. And then the leftover parts, right, 2x and the plus 3, that is the other factor. And that's it. This is it. Final answer, 3x plus 1 times 2x plus 3. So the idea is that if we were to distribute this, right, FOIL this out, we would end up with 6x squared plus 11x plus 3. Kind of interesting. Let's see another example of this particular method, the AC method. Okay, here we have 12x squared plus 17x plus 6. So I want to come up with two numbers that multiply to make a times c. So in this case, we have, again, a, b, and c. So A times C, so 12 times 6. 12, 24, 36, 48, 60, 72. So 72, and we needed to add up to 17. All right, going through the list of 72, right? 1 and 72, 2 and 36. I'm going to skip a few. One that pops out of my mind is 8 and 9, right? 8 times 9. 8 times 9 is 72. And then, as we're going through this list, we try to see which ones add up to 17. Notice they're both symbols are plus. So I know that I don't have to worry about the negatives. If one of these was negative, then you would have to consider the negative factors of 72. So 1 times 72, that doesn't add up to 17. 2 and 36, that doesn't add up to 17. However, 8 and 9 do add up to 17. So those are the numbers that I'm going to split 17 into. And it doesn't matter which one goes first. You can put whichever one you want first. It truly does not matter. That's the beauty of it. All right, 8x plus 9x, or whatever the variable is. In this case, it's x. All right, we have plus 6 plus 12x squared. Again, we split the 4 terms down the middle in front of the second sign. And now we look at the GCF. What number is common to both? So what number is common to both 8 and 12? They're both even. 2 will work. In fact, 4 will work as well. So 4, and there's an x. So 4x. So then what's left behind? That's the question. So 4 times 3x, 4x times 3x, that gives me 12x squared. And then plus 2. 2 times 4x gives me 8x. All right. For the right-hand side, again, keeping in mind, I want 3x plus 2 to show up. So what number is common to both positive 9 and 6? Remember, you always want to look at the symbol. If it's positive, you're pulling out a positive. If it happens to be negative, you're going to pull out a negative, typically. All right, so this is 9 and 6. So for sure, 3. What about the variable? Well, there's only one x, so we can't pull out anymore. This is going to be 3x that's left behind plus 2. Again, if you distribute, 3 times 3 is 9, and 2 times 3 is 6. So notice 3x plus 2 is definitely matches. So that's going to be one of our variables, or one of our factors, rather. And then the parts that are outside left over, 4x plus 3, that's our other factor. 4x plus 3. And here are the two factors of 12x squared plus 17x plus 6, using the AC method. I guess one thing that I kind of glazed over, the little x method that we use, I mean, you might see in some methods, they write the plus 8 and the plus 9 here. But I don't know, that's kind of irrelevant at this point, only because you're writing them again over here to the left. But that's just a technique thing. I wouldn't worry too much about that. As long as you know what to do with the numbers, that's the best part. Okay, so that's the AC method. Let's look at slide and divide. Okay, so this particular technique, the slide and divide technique. When I first saw this, I almost immediately fell in love with it. And I didn't learn it until much later in life. So compared to the AC method, right, there's some things that are similar, the way it starts off, but then the way it ends is completely different. Now, there's really no, the way I explain it and the way it's explained, like it looks like magic, right? Like it's going to look like tricks. Like it's going to look like, why is this working? Or like, what the heck is happening? But, sometimes you just got to roll with it at this point in the game. So I'll show you an example. So let's go with 3x squared plus 7x plus 2. So I want to factor this using strictly the slide and divide method. Okay, so the part that looks similar to the AC method, we slide the A term over, right? So we multiply. So this is the sliding part, and we multiply. So 3 times 2 is 6. So we have to figure out what two numbers multiply to make 6 that add up to the B value, which is 7. So this looks just like the AC method starting out. So we start running through all of our factors, right? 1 times 6, 2 times 3, 3 times 2. All right, and they're both positive. So which ones add up to 7? Well, 1 and 6 do, 2 and 3 do not. So 1 and 6. All right, so here what's happening is that this is the quadratic that we're solving. So what happens is the 1 and the 6 drop right into parentheses. So this is going to be positive 1, and positive 6. Okay, so that was the sliding part. Now comes the dividing part. So one thing I learned about this particular method is the dividing part is the most missed step, right? It's the most missed step. Is the sliding part is the easy part to remember. It's the dividing part, the dividing it back out. What we need to do is that because we multiplied by 3 right in the beginning, we have to account for that. And the way we do that is we divide both of these numbers by 3. You always reduce as much as possible. So here we see that 6 and 3 reduces. So this is going to be x plus 2. And notice 1/3 does not reduce anymore. 1/3 does not reduce anymore. So what we do when it doesn't reduce anymore, we take this number and we swing it up in front of the x. So there's the magic I was talking about. There's a reason behind it. It's just I don't want to go into that. We just do what we do, right? So this is going to be 3x plus 1. And now this is the factors of 3x squared plus 7x plus 2. All right, let's try that with another example. Again, slide and divide method. I think most people like this method only because compared to the AC method, right, it's a lot less work, right? It's like splitting it up and factoring it. But I don't know. I like the AC method. I like the slide and divide method, like right from the jump, just because it was brand new to me, and it was just different, right? I liked it. Sometimes though, it doesn't always work out, which you'll see here a little bit later. All right, see another example of slide and divide. Okay, here we have 4x squared plus 19x plus 12. So again, A times C. So 4 times 12, 24, 36, 48. So numbers that multiply to make 48, again, both positive, that add up to 19. So 1 and 48, 2, 24. Does 3 work? 3 and 16. All right. That's it. That's the one. So notice we slid this over. So x squared plus 19x plus 48. Looking for the factors of this guy. This is x. The numbers drop right in. Plus 3, plus 16, And here comes the divide part. So you have to divide this by whatever the a value is. And then you reduce as much as possible. So one of these typically will always reduce cleanly, right? 16 divided by 4 is 4. However, 1, typically not so much. That bottom 3/4 doesn't reduce anymore, so it moves up. Okay. And that is the slide and divide method. I guess do I want to show you? That's the question, right? Kind of like the reason behind the magic. So when you have the thing you're looking for, right, are the two numbers that when you multiply, they equal a times c. Right, I'm looking for two numbers always. Then I'm looking for those same two numbers that when you add them together, they equal the b value. Right, that's essentially what we're doing. Like two numbers that multiply to make the product of a and c, and right other than a and c, and then the exact same two numbers that add up to b. So when you find those two numbers, so if you're a formula person, this is basically what's happening. But I know it kind of looks crazy, right? But notice what's happening is you have to divide by the a. That's what's happening. And when it doesn't divide cleanly, the a goes in front of the x. So notice if you were to distribute this, the 1 over a and the a would actually cancel out. So that's why one term, right? So if you look back at our example here, one term typically doesn't have a number in front. I mean, technically there's a 1, right? But yeah, so I wouldn't get too hung up on the reason why, like I mentioned earlier, but just know that it works, right? It's the result of something awesome that you can just take advantage of every time. So that's the slide and divide method. Okay, now let's look at a special case. So we call this special cases. All right, so if you can notice a difference of squares, this makes life easy, particularly because one, where do I want to write this? This has to do with binomials. So if it's a binomial, you always want to look for a difference of squares. So for example, here we have an example. Was this example 5? All right, so 9x squared minus 16. So the idea is this. If I have a squared minus, right, minus is a big one, right, because that's a difference. That's what difference means, a difference of squares. So b squared and a squared. So if I have a difference of squares, perfect squares, then a plus b, a minus b. This is the result. However, you have to be able to identify the a and the b. That's the big one, right? Like they've got to be squared. And if they are squared, you can kind of break them out of the parentheses that they're in, or like the form that they're in, and then make a plus b, a minus b. But only if they're squared. So notice identifying perfect squares is the key. Well, here we have 9 and 16. 9 is definitely a perfect square. It's 3 squared. X squared is still there. Minus, that's the key, right? If this was plus, we wouldn't be able to do this, right? If this was plus, only if it's minus, right? A difference of squares. There's no such thing as a sum of squares. And then 16 is really, I'll use a different color, 4 squared. So if you can notice, right, that you have perfect squares that can be written as squares, then this is going to work out. So there is one little thing that's happening here with the 3 squared and x squared. We can almost, I hate using the word factor, but we can kind of factor out the square. That's not necessarily a thing, but it gets the point across, right? I can pull out a square in a sense, right? Because when you apply the square, you get 3 squared x squared, because it's like the square, the exponent applies to everything inside. Okay, so then minus 4 squared. So notice the a is the part that's being squared, right? This is your a. And then the number 4, we can call this the b. So if a is 3x and b is 4, I'm going to take 3x, I'm going to take 4, and I'm going to do a plus b, a minus b. So this is going to be 3x minus 4, 3x plus 4. Now you may be asking, a common question right here is, where'd the squares go? Right? So I'm rewriting the squares in its factors, because if you were to start to distribute and FOIL this out, things would cancel, and then you would end up with 9x squared minus 16. That's what would happen in the end. So a squared minus b squared specifically factors into a plus b, a minus b. Now you could write the a minus b first like I did here. That's fine. See another example. All right, example number 6. So another difference of squares example. So if we have 25 x squared minus 49. So right away, you have to be able to identify, like, it's got to be able to jump out at you, right? The perfect squares, that is. So if the perfect squares jump out at you, that's what you want to happen. So you got to recognize these numbers. So this is 5 squared x squared minus 49, which is 7 squared. So typically there's a variable involved. And right now, this is the ideal case because it's already squared. Sometimes it's not squared, and it could be a higher order, right? An 8 or a 6. You always want to rewrite it so that it has a square in it, which we'll cover that later. So this is going to be 5x squared, right? That's my a value, minus the b value, which is 7 squared. Again, this is a, 5x, and this is b, 7. So once you identify a and b, you can go straight to a plus b, a minus b. So that's going to be 5x plus 7, 5x minus 7. And there it is. So notice, right, how the a and the b are separated by a plus and a minus. We call this a conjugate pair. So this particular word is going to come up a lot in the next couple of lessons once we get to complex numbers. But conjugate pair, this is the first time that we see this particular idea. So it's in a difference of squares. All right. The last example that I want to look at, perfect square trinomial. So here the idea is this. So let me just show you an example. So if you were trying to factor this, right, what would you do? Either the AC method or the slide and divide. For sure, 100% all day. And then you would just start going through the process, right? You just start going through the process. And then you would eventually get to an answer. However, sometimes, right, if you notice, now, you always got to be on the lookout for perfect squares, right? Because, check this out. 4 is a perfect square. 9 is a perfect square. So this is really 2 squared, 12x, plus, again, 3 squared. All right, so the idea, and this is, I mean, I'm not expecting anyone to see this particular way that I'm doing it, and all of a sudden you get it overnight, right? it definitely does take repetition and it does take training. But eventually, once you see it, like, it's hard to unsee it, right? So what's happening is that, so I'm going to pause here for a second because I want to demonstrate something, right? The reason it's a perfect square, or we call it a perfect square trinomial, right? Like, if you have a square, that means you're multiplying it, right, in terms of area. All the sides are the same. So 2 times 2, 3 times 3, right? That'll give you the area. But what if, right? What if it wasn't a number, right? What if it was variables, right? As in this case, a plus b times a plus b. So this is really the area, that is a plus b times a plus b. When we factor this out, or not factor this out, when we distribute, this becomes a squared plus ab plus ab plus b squared, which is a squared plus 2ab plus 2b squared. So no matter what a and b are, this will always be the outcome. And what this means, right, I have a plus b times a plus b. This is really a plus b squared, right, because there's 2 of them. So what we learn, right, pattern recognition, the part that we catch on to is that if I have a binomial, right, 2 terms, a plus b, and I'll always have this product on the right. So instead of, I wouldn't say instead of foiling it out, that's going this direction, right? So I'll cover that in a second. So a plus b squared, it'll always be a squared plus 2ab plus b squared, like no matter what a and b are, right? This will always be the product. So the thing that I'm looking for is the a squared plus 2ab plus b squared. So you can kind of see that a is 2, b is 3. Now, will it always work out? That's the thing. No, it won't. It's because of this middle part, right? The 2 times a, so 2 times 2 times b, or 3. So what is 2 times 2 times 3? Well, that is in fact 12. So because it's 12, this is a perfect square trinomial. And so this actually turns out to be 2x plus 3. 2x plus 3. Or simply 2x plus 3 squared. So I know, but that's a bit of a stretch, right? Like a lot just happened in like the last like 120 seconds. So let's kind of see if we can break that down again. Like, quick little recap. So the idea, if I have a binomial, right, what a perfect square trinomial would be, is if I have 2 terms, binomials that are the same, being multiplied, right? So a plus b squared. We know that the result will always be a squared plus 2ab plus b squared. So if I can recognize that, right, that's a hardcore if, right? Because otherwise we could do the AC method and we could have been done already if I hadn't been explaining all this. But sometimes you can recognize that, okay, I have a perfect square, 4, perfect square 9. Let me just see if it works, right? So then you take, obviously the A and the B are the easy ones, right? Because those are the obvious ones, right? 2 is obviously the A, 3 is obviously the B, but it's that middle part that I got to check. right? A times B times 2, or 2 times A times B, does that equal that middle term, right? If this, say this had been 14, all right, if this was 14x, this would definitely not work because 2 times 2 times 3 is actually 12. So if this was 14, this is not a perfect square trinomial. It just so happens in this case that it works. Let's see if we can see another example. Like, let's clear the screen, clear our minds, and this will be the last example, number 8. Okay. Now, again, AC method, slide and divide will work lovely every time. But if you can recognize, right, that there's a 1 in front. There's a 1 in front. Right, 1 squared is still 1. 5 is really, oh, I'm sorry, 25 is really 5 squared. So if we look at the middle term, remember, do you remember the shape of the formula? A squared plus 2ab plus b squared. So in the middle, we're looking for 2 times, right, because 2 is part of the equation, 2 times a times b, which is in fact 10. Right, this is exactly 10. So this is a perfect square trinomial. So my a value, right, this is my a, and this is my b. So we can go straight to the answer. In fact, we know that it's only going to be one answer, and the answer is going to be squared. It's x plus 5. Right, because this was x plus 5, x plus 5, which is x plus 5 squared. So, I mean, I did it in a fraction of the time, right, then of figuring out what numbers multiply to make 25 that add up to 10, split it, GCF, right? Like, I mean, these things take time. So you can see how this is like super powerful to just go straight there. I think that between these 3 methods, or recognizing these 3 methods, you should get good at. I do want to mention one thing, because here we did a plus b and a plus b. This could very well be a minus b. So let me just show you that, so you have that like in your back pocket. So the a squared plus 2ab plus b squared, that, just burn that into your mind. But a minus b and a minus b, this is a thing also. So this is going to be, right, the area, right, a minus b squared. So if you can recognize this, this is going to be a squared minus 2ab plus b squared. So it looks very similar. The only difference is that there's a minus right here. So with this being said, right, going this direction, there is a nice little trick that's worth mentioning. If you're in a pinch, right, and I want to multiply 2, I want to square a binomial quickly, which you'll see this in my future videos, or past videos rather. And instead of writing it out twice and then foiling it out, you'll see me do this design. So right, a times a is a squared, b times b, b squared, and then really 2 times a times b. So 2 times a times b. And that's literally what we have up here. It's just out of order, but it's all being added, so it really doesn't matter. And the same goes for, watch, you might have to like rewind that a couple times. The same goes for minus b, or a minus b. So a times a gives me a squared. Negative b times negative b gives me positive b squared. And then 2 times a times b. So 2 times a times negative b. So minus 2ab. And that's exactly this guy right here, just out of order. So those are the two, I guess, tips for the day. Hopefully this helps someone. I know this is a little long-winded lesson, but I feel like it's very useful. All right. Catch you guys in the next video.